Hello and welcome to our webinar, a demonstration of an interlocking design automation solution. It's now time for us to start, but before we start the webinar, I just want to inform you that you have the opportunity to ask questions. You can ask questions whenever you want, and there is a question mark icon on the GoToWebinar control panel. Just click that and you can type in your questions. We will focus on answer questions in the end of the webinar, but if there is any questions that are obvious that we need to step in and answer during the webinar, we will do that. So please look for the question mark icon and take the opportunity to ask questions. We are the only ones that will see your questions, so the rest of the participants will not see them. So I would like to hand over to today's speaker now, Mr. Jesper Karlström from Prover. Welcome, Jesper.
Thank you, Lars. Yes, I'm Jesper Karlström. I'm responsible of the project delivery at Prover, so our services department. I've been with Prover since 2008. And I'm here today to present to you the way we think that signaling design automation should be done. It's the so-called Prover Trident process that we offer. It consists of 3 parts, which I will cover, doing general specifications, doing specific application engineering, and doing sign-off formal verification in the end. In the end of this webinar, I will give a few recommendations on how you can start your journey towards a more automated design process. There will also be questions and answer sessions in about 30 minutes from now, based on the questions that you add in the way Lars just described by clicking the question mark in the control panel. What I want to show you is a process where you can depart from some signaling principles and construct an interlocking system that follows these principles. So for the sake of a demonstration, we have come up with some mock-up signaling principles. The idea is that in different areas of the world, for different lines, different states and so on, there might be different signaling principles, and our solution is tailored to make it easy to adopt your signaling design principles to the area where you want to operate. So to show this, we have these mock-up principles. I will not go through these in detail because they are not the focus of this webinar, but I think it's necessary and good to understand at least what the signaling aspects say. We have here only one type of signal. It can display 3 different colors in the upper light and 3 different colors in the lower light. The upper light tells if the driver is supposed to stop, or can proceed at a restricted speed, or can proceed as an unrestricted speed. Red, yellow, or green, depending on the state. If it's an unrestricted speed from the signal will also display the second light as a distant aspect. So if it's red, it means that the next signal is at stop. If it's yellow, it means the next signal is at a restricted speed. And if it's green, it means the next signal is at an unrestricted speed. The content of this demo will focus on the specific application process, configuring a station with mock-up signaling principles, doing some simulation, both interactive and scripted simulation, doing formal verification, and doing code generation. Then I will show the certification process where you use a standalone formal verification tool to prove that your system is safe. In the end, I will touch upon how you make changes in the generic application. Not so much because this webinar is focused on the specific application engineering. The generic application engineering is not very different from the ordinary process based around generic applications. The main change we offer is a smoother specific application engineering process, which also makes it easier to make changes in the generic application. That being said, I want to switch to the demo. We have this program here, Prover iLok, that is an ordinary Windows program. When you open it, it has almost no built-in signaling principles, no symbols. But you start a new project by choosing a name for the project and some principles. So let's call it sighting, because I want to do a simple sighting project here. I put it somewhere, can have it on the desktop, and I need to choose signaling principles. For this webinar, I want to choose demo principles with a certain version here, the latest I have, 2.3.1. So make this choice and Prover iLok will load the signaling principles demo 2.3.1. It will also load all the dependencies. So these principles can depend on various other principles that are also loaded. You can see now that some symbols have appeared here based on the signaling principles we chose, but also a number of packages are loaded here. Normally we can complete this form with the various things like the customer and the version and so on, but I don't have to do this now. To start now the specific application process, we need to configure the track layout, and we do that by drawing like in a painting program. So I want to make a sighting station. I draw the tracks. And when I connect tracks like this, Prover iLok will make switches for me. I want to put out some joints for track circuits here. Like this, then I put some track circuits. You see that there are names here, so I can choose a different name, but I don't need to change anything here, so I just keep the suggested default names. Then we put some signals. I want an entrance signals here, entrance signal here. And I want exit signals here. Exit signals here as well. An entrance signal here. You can see the little red dot showing where the signal is interpreted as its logical place. Okay, let's save this now. You might notice that this is a bit off. If you click it, you see that the red dot is not exactly to join, so I can move it like this. And then I want to set out the controller for this station. Let's call it sighting. And some orientation arrows saying that we have two different directions. Perhaps these can be called east and this can be called west. Okay, so this is the configuration of the tracks. Normally for real interlocking, one not only have configuration of the track layout, but also some complementary tables. In this demo project, we don't have that, so we can just click here now and generate logic for this specific application based on the generic principles that are loaded in the beginning. So for example, if there's a signal here, it will create routes according to generic principles from this signal. until the next facing signal, and from this signal until the next facing signal here. All these principles have been defined in the package I loaded from the beginning, and we will look at that package in the end of this demonstration. Now the interlocking logic has been computed by this program based on the generic application and the track layout, so I can start a simulator to try the interlocking. If it's a real setup with a specific application engineering aim, then I suggest that you use two different screens, one for the track layout and one for the simulator window. But for this demonstration, I will hide this window behind the other one and show it only when I need it. I started now the interlocking, so you can see that the signals are at red everywhere, and I can try things by requesting a route. We can see that the switch moves, a route locks here, and the signal displays proceed at an unrestricted speed. So here there is now a signaling principle I loaded in the beginning that says that if the route is over a switch in the divergent position here, then you're not allowed to use green. You're supposed to use yellow. So because of this switch position, it knows that it's supposed to have yellow aspect. If we request a route from the other end and have a straight route, then it will be green, unrestricted, because this switch is straight. The lower light here is red, because when there is green, there is always a distant aspect, and red means the next signal is at stop. We can also request a route out here. It's now gray because it's stored, waiting for this route to release. And we can try and run a train along this route. Clicking there, see that there is a red occupancy on the track. And when this track is vacant, the route is released, the switch is thrown, and another route is locked here. We can see now that this says green, 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 green. And the occupancy is here. We can also try and just click on a track to see what happens if you occupy a track. If you occupy here, you can see the signal turns to red. And if we remove the occupancy, the signal stays at red, because according to these signaling principles, there is a notion of a consumed route, that if you have had an occupancy on the route and the signal has turned to red, then it's not allowed to turn back to green unless you release the route. So we try to release the route. Oops, sorry, wrong route. Release this one. It initiates a release process, and we can request to have the route locked again when it has been released. So immediately when the route is released, it will be locked again, and the signal is up to green again. Okay, this shows so far that based on the generic principles that I loaded and the track layout, I can construct an interlocking, and I can run it in the simulator like this. We offer also a simulator that can run predefined test cases. If you start here and run, it runs through all the test cases that have been predefined. In this case, we ran 42 test cases. So based, for example, on standard procedures for principles testing, you can predefine test cases in the beginning. For example, you can say that for each route, you're supposed to try certain things, and then the test is repeated for each route. So if you make a change in the generic application and want to ensure that you didn't damage anything, you can rerun the tests quickly and see that everything works still. We then also have built-in formal verification. So by clicking the verify module here, we can see all the requirements that have been implemented in this case. Not so many because it's only for demonstration purposes, but still a number of them to try. And again, each requirement is supposed to be proved for each route. In this case, if it's a requirement about routes, there is also a requirement for main signals. You can see the explanation here, and it's supposed to be proven for all signals. So by clicking run, I run all the requirements, and in this case it's very quick, 0.4 seconds for 300 requirements. Normally in a real project it takes longer, but still for a station of this size it's usually about 4 or 5 seconds to prove a set of real requirements. This is much quicker than much other formal verification you have probably heard about, and that is because when you do model-based development like this with a tool that has integrated formal verification, then during development, if you have any deviations here, you look at the counter models you get and you fix whatever is not functioning in the design, and when the design works well, it's usually very easy to prove that it follows all the requirements. Okay, let me turn back to and sum up a bit what we did. Well, actually, I have something I forgot to do, the most important thing perhaps. When we are done both simulation and formal verification, it remains to also generate the code for the interlocking. So I click the coder module, and in this case, for the demo purposes, we have C code as the target language. But there is support also for many standard hardware platforms in the railway industry, such as Microloc, VHLC, Westrace, IVPI, General Electric, Tempo, and so on. But here it's C code, so we generate and we get, oh, sorry. Oh, I need to run it from, so that, I need to find it. Let's do it like this. Let me find something I did just before here. I made a mistake and moved something on my computer, so now I cannot generate the code. Sorry. It should work if I do it from here. So it's the same layout here, but I drew it before. The C code generator presupposes that you have some templates in place, and I made the mistake of moving everything. So if I run now, it should work, I think. Yes, here are the C code. So all the files for the templates were missing. I have here in various folders the different code snippets that together build up the interlocking. Okay, to sum up what I did in the specific application process, we configured the station. Because it's only a demo, we only had track layout here, no complementary tables. Usually there are also tables with configuration data used, and the division between table data and drawing data is essentially up to the customer. It's very convenient to use the drawing for such information that is normally in drawings, such as tracks, signals, wayside objects, and so on, and to use tables for data that is not well represented as geographical data. for example, time and values and other stuff like this. I showed some simulation. I think it's very important to have both interactive simulation and scripted simulation. Interactive simulation so that you can try things on an ad hoc basis, and scripted simulation so that you, in a systematic way, can run lots of test cases easily. For the formal verification, I use this to prove that all the safety requirements are fulfilled. It is sometimes considered a problem to have the same tool for doing both design automation and formal verification, and we acknowledge this problem because of the dependency. It's not easy to argue that the formal verification is independent from the design automation. So therefore, we also offer an independent formal verification, so-called sign-off verification, which I will show in a few minutes. I then did some code generation, and in that case, you don't have to do anything manually, just push a button and you get your files. One more thing should be done. We need to generate files for the certification process. Sorry, here it is. So we generate certification data that will be used for Prove Certify. Okay, so now the next thing I want to show you is how you do when you want to approve this. So you need to use an independent tool for formal verification, and what we use here is Prove Certifier. Let me visit where I have everything. So I open this, it's a terminal, it's actually Cygwin, which is a Windows program that mimics the Linux user interface. And I do this only to demonstrate here to you how I use this. Because for the safety critical applications, such as sign-off verification, we have decided to do all these products in Linux. So we offer them on our servers, for example, but also customers can have them installed on their side. I need to transfer the files for this independent verification. So I do a secure copy, and I need to send the first the logical model of the interlocking. I also need to send the C code generated and the certification data. All this is supposed to be sent to the server. The server is called Prover Online, and I put it in a folder called demo. Here we go. All files are transferred. So I visit the server and the directory, and here I have my files. So I can now run Prove Certifier. It's called Demo Certification Tool here. It's essentially Prove Certifier, but with some configuration made to tell it that it's C code and so on. I want a verbose output, and I need to tell it its logical model of the system is here. The C code is here. And then all the requirements it's supposed to try are here. Now it's running. It then runs the logical model, compares it to the C code, ensures that they are equivalent and that they fulfill all the safety requirements. The proof of this is stored in the proof log, and there is a check of the proof log in the end. So this is essentially doing the same thing as the formal verification that was built into ProveILOC, but this time it's done in an independent way and a bit more thorough way. Okay, So the certification flow, to sum up, normally we have two code sources. The first code source could be generated source code, as in this case, C code. It could also be imported code if you want to formal verify code that has been changed, for example, manually, or has been even manually written. Then we use the second code source. It could be, in some cases, compiled binary code or the logical code model. And in this case, it was a logical code model as the second source. We have generic safety requirements, and these are written in a logical language and reviewed at the generic application level. So it's a tough review to do, but you have to do it only once. You don't have to review it for each station you make. For each interlocking, however, you need configuration data, and this data is supposed to be checked at the specific application level. This shows now all the input data you need to give to Prove Certifier, and you get out from this a result of the formal verification. What I did was I collected relevant files, transferred them to a Linux computer, I ran Prove Certifier, and the only thing that remains here for this to be a real thing is to review the configuration data. It might look a bit heavy to have a Windows program as the basis for the work, but have to turn to a Linux computer when you do the sign-off verification. But I want to stress that this Linux computer is only used as a final sign-off verification. So you normally use the Windows program many times during the project, and then when you're done, you run Prove Certifier. And in many projects, this is even done by a different person. ProRILOC is done by the application engineer, and running Prove Certifier is done by a safety reviewer or safety assessor. Okay, the generic application process I want to show a bit too. Let me close here, and I want to show you what we can do if we want to change some principles. Let me open the demo package that I used in the beginning. Here are all the files with this for the design, the generic design, and I want to show you the switch file. So switch meaning the same as point. What is normally called point in British English is called switch in American English. The same thing. So this is an example of how it looks in the generic application. It's written in predicate logic, but there is a simple object orientation, object-oriented type system on top. So here we define a number of functions, like what it means for a switch to be placed to the left, placed to the right, and so on. And this is essentially only exporting variables, but then the real logic comes here. So for example, the logic for throwing the switch left is written here. What does it check when you want to throw a switch to the left? It checks, in this case, that it's not locked. This means not, and this means and. So it's supposed to be not locked and not already placed to the left. No idea of placing the signal to the left if it's already there. There must not be a request from the human machine interface to throw the switch to the right. And there is also a notion of a switch being thrown by a root. So if you request a root that needs the switch to the right, it will be thrown to the right. So these are negative checks, and then there are two reasons to throw the switch to the left. This one if there is a manual left request from the human machine interface, or the switch is needed left by a root. So this is the OR sign. If we imagine now that there is someone introduces an error here, for example, a copy-paste error. It says right by root instead of left by root. Let's show what is. Let's see what happens here if you open the project when you have made such a change. First, whenever you open a project, this application will check that there is no integrity issues with the generic application you use, because there is a fingerprint that can discover if there are changes. And this is what happened now. It tells you that there is some change here in this file, implementation of the switch. But we choose to ignore that now, and then we simulate what happens. So again, what did I do? I introduced the typical error here. It could be some kind of copy-paste error. The principle for throwing a switch to the left was changed so that you can still do it manually, but if a root needs to switch to the left, it will not be thrown automatically anymore. So for example, if I throw this to the left from the HMI, I can simulate this, it will work. It's thrown to the left. And I can throw it to the right, still works. But if I request a root, it will probably not work. It's stored the request, but it cannot lock it because this switch isn't thrown. So let me throw it manually instead. Now it works. It's thrown because I did it manually and it locks. Now, if we try to run the scripted tests, it will discover that certain tests here do not work anymore. Some routes work perfectly fine, but this one does not. So it's the same as we tried from G1 to G4, doesn't work anymore. And another one from G2 to fringe exits S1. And that is this one. Doesn't work either. So we can actually try it. We can run this test and see where it gets stuck. The test is ran according to a test program now. So occupy start track, request the route becomes locked within 10 seconds. This doesn't work. So if you click here, you see it has been stuck here. The route is requested, but it doesn't lock because the switch never throws. If you run the formal verification requirements, you will notice that they all pass. No problem here, because there is no safety requirement involved in this. You never reach an unsafe state because you never get the route locked in the first place. So it's not a dangerous error I introduced. It's a functional error. It will not be, it doesn't violate any safety requirements, but you can still find it using simulation. Let me make another change here just to demonstrate. I revert this. And then I introduce instead a safety critical error. So I take away the first line here in the locking equation. The principles here says that there are 4 reasons to lock a switch. The first is if the track where the switch is, if it is occupied, then you're not allowed to throw the switch. Switch must be locked. The second one is if some route over the track requests the switch to be locked, it must be locked. Then there can be a flank protection purpose and a front protection purpose. Let me make these changes. This means comments, so I take away the first here. If I occupy a track, I can still throw the switch. And this should be violating a safety requirement. Let me open it. It warns about integrity issues, as usual. And then I start simulation. So I reverted here. This should be okay now. But in some cases, the switch will be possible to throw, although there is an occupied track. And this is a dangerous error, which might cause some kind of derailment. We don't want that. So we can try it. If I occupy this track, I can still throw this now, I think. Yes, I can still throw the switch. If I run all the test cases, they will probably pass because they don't. Yes, they do. There is nothing functional that is prevented from working because of this new check here. But it's a dangerous check, so you should probably see it in the formal verification here. If you run the requirement, it falsifies one here. If you click on the switch, it says a non-vacant switch must not alter its position. Here it says it's perfectly possible for a non-vacant switch to alter its position. If I double click, I can ask about a case where this happens. So it shows me a case where the switch actually throws, although it's not vacant. So you can see the square here means it's not fulfilled. So it's supposed to be vacant, but it's not. It's a square. And here I can see it's now placed to the left, although it was not placed to the left in the previous cycle, -1 here. So just before it was not, now it is. So it's a flank in the sense that placement to the left has just occurred, even though the tracker is vacant. If I want to investigate this, I can click and follow the logic and see what happens. Here you can see throw right is marked. Yeah, so you can follow like this. Okay, let's sum up again. I didn't talk so much about the generic application process in itself, but I showed how we could change a few principles and have quite some impact. Simulation showed how a small change turned out to have big unwanted impact in a functional sense, and formal verification showed problems in other cases. I haven't been focusing on the generic application process because there are no big differences compared to any process that is based on a generic application. We do think, however, that having a good specific application process is important if you want an effective generic application process, because you use a specific application process to try what you do all the time. Now to some recommendations, what I think you should do if you want to do something like this. The first is to integrate tools as much as possible. I think it's a mistake to have a separate development. Of course, we need always separate teams, a development team and a verification team, to make sure that there is an independency. But it's very good to provide the developers with some tools that they can check their logic, because if they have means of simulating and verifying that what they do is correct, then they will give a much better system to the RAMS department eventually. So for the same reasons, all the V&V tools should be available to all involved engineers. It's rather common to have only a simulator in the basement, for example, have a dedicated room for this, but I think it's very good if you can build a simulator that everyone can have in their own laptop. If you automate the process, it's very important to bring your staff on board. By this, I mean that a very common question is, okay, if we automate a lot, what should we do with all the staff we already have? You will still need staff. The senior staff can work with defining the generic signaling principles, for example, as in the language I showed before, but if they are not comfortable with programming predicate logic, they could work with writing principles in plain English, for example. And you can use other staff for formalizing the principles. Bottom line is that you will be able to deliver more projects with the same staff. To start a generic application development, you need some specifications for the line or the area you want to signal. A good specification can be divided in 4 pieces. The first one is the object model. It needs to be very precise, but it need not be very deep. An object model is essentially a list of all the objects you will have, like we will have switches, we will have signals, we will have level crossings, track crossings, balises, and so on. And for each such each such object, you need also to specify the inputs and outputs. So all the bits that are supposed to be received from such an object, and all the bits you are supposed to send to such an object need to be specified. And this is very important. It's an interface, especially if you will be several teams involved. It's very important that all the teams have a common understanding of the interfaces of all objects. The design principles are the fundamental principles strictly specified. And then above that, there are always fine-tuning, and that can be made in a more agile way. So you need to specify what you really think is important to follow, where there's no room for creativity, but you need to stick to certain things. They have to be specified carefully in some document, and as much as possible that need not be specified in this way should be left open to the engineers to come up with in an agile way to get the most efficient process. You need to specify also tests, that is, use cases, scenarios written early for test-driven development. A very good way of specifying how you want the interlocking or system to function is to specify how this could be tested. So for example, if for each route I want that it should be possible to request it, and then if you wait a few seconds, you should see that the signal clears, and so on. This can be specified, and it works both as a way of explaining how you want the signaling system to behave, and also a way to specifying how you want this to be tested, that you actually got a system that fulfills your requirements. Finally, you need some safety requirements that you use for formal verification, and by having these requirements early, you can also use formal verification in an iterative way during the project. If you want, you can let us or someone else write the specifications. You need not do that yourself. You can provide us with sample programs, drawings, and whatever you have. You need to allocate an expert who can answer all questions. You probably will have to review also, especially the object model, which has to be negotiated quite early in the project. Otherwise, except for this, we could help if you prefer. Then you need to formalize the specification, and this we can also do for you, or some other consultants can do it. You need to allocate an expert who can answer questions about your natural language specification in the case it's not very precise, for example. So the first step, if you want to increase automation in your process, would be to have a meeting. We can have a meeting via Skype or face-to-face if you prefer. 1 or 2 hours would be enough, I think. And then we'll review together your current process and your challenges. And after this meeting, you will already have a plan for how you can increase your automation in your process. The first thing here, interlocking design automation inspiration workshop, is something we could set up if you need to know more about the prove trial and process. For example, you might need to involve some engineers at your company. So just contact us if you want to have such a workshop, and we'll set it up, and you will have a roadmap for how you can change your current process. We can also set up a more business-oriented business case workshop if you want to know more about how much savings you can do by automating your process. Okay, I think it's time for questions and answers.
That's time for Q&A, Jesper.
Yes.
So thanks for that. So everyone, look for your question mark icon on the GoToWebinar control panel, and you can ask questions. So we have a couple of questions that have already come in. Why don't you have built-in signaling principles, Jesper?
Simply because in our experience, end customers have so many opinions about their signaling principles. So it's a very tough thing to come with pre-cooked signaling principles and suggest that they use them instead of their traditional principles. They are, in some countries, it's even by law. So we decided to create an application where you can easily define your own principles instead of having predefined ones.
Okay. Another question. Which hardware platforms do you support?
It's besides some general purpose languages such as C or Ada, we have been working with Marklock, Reach LC, Westrace Mark 1 and Westrace Mark 2, IVPI, VPI, Tempo, Electrologix, yeah, quite a few. And the most of them are in this kind of segment, so originally meant for manual programming for a specific application, but nowadays we do it with design automation, but it's the same platform in the end.
Okay, yeah, that was 2 questions that we received so far. Please type in your questions using the question mark icon, and here comes another question. All right, here it is, Jesper. How about non-vital logic? Do we understand the question?
Yes, we do. Yes, we normally, when we do code generation projects, we generate both vital and non-vital logic. And it can be decided in the code generation step that you put the vital logic in one controller and the non-vital logic in another controller, for example. So it's really no difference. It's the same process for both.
Okay. All right. Let's see if we have any more questions coming in. Yeah, we just got a thanks for that answer. So no, we don't have any more questions this time. So if you don't have any more questions, I'd like to say thanks to everyone that participated on this webinar this afternoon. And I also would like to say thank you to Jesper. Of course, you will all receive an email after the webinar with contact information so that you can continue to ask questions and get in touch with Jesper and Prover so you know how to proceed. So thank you, everyone. Thank you, Jesper. And if you're on Central European time, have a great late afternoon and evening. So bye-bye, and we close down the webinar for now.